All right. Hello, everyone, and welcome back. I think we're entering week 3 of MCT4C, but I guess I should probably start recording this first. So let's go ahead and do that.
Recording in progress.
Hello, everyone, and welcome back. We're now entering week 3 of the course as we are going through MCT4C. This is lesson 5.2, meaning that we're in unit 1, somewhere in the middle of lesson 5. And we're just today we're going to be going through not linear and quadratic, but in fact cubic and quartic functions. Now it's worth noting that I said lesson 5. If you've been having a look through it, it's quite lengthy. It makes a lot of assumptions, hence we got to spend a little bit more time on this. And so we're going to be again look similar to what we did last time. We will be looking at the degree and identification of polynomial functions. In specific, we'll be studying cubic and quartic polynomials. And if we have time, we're going to be expanding and simplifying polynomial functions. If not, we'll cover that tomorrow. It's not a big deal. In general, we'll know that things are going well if you're able to understand cubic and quartic polynomials. And when I say understand, I mean, say you're able to look at this equation and roughly know what that cubic should look like. Okay, that's what we mean by analyze and understand. So in general, we're going to be going a little bit more abstract. So in general, polynomials have this generic structure. A sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1 plus a sub n minus 2 times x to the power of n minus 2 plus dot dot dot. And all this means is that in general, we're having a look at polynomials like, say, 7x to the power of 4 minus 3x to the power of 3 plus 2x squared minus 5x plus 1. So if you notice here, we start off n minus 1, n minus 2. That just means that the powers drop every time. And the reason why we call it a sub n minus 1, a sub n minus 2, and so forth, is because just to show that these are different coefficients, and they could be different. Okay. So previously, we studied linear and quadratic functions. So we had a look at ones like, say, y is equal to x minus 2, y is equal to, say, 3x squared plus 4x minus 1, or ones like y equals x, in brackets x minus 2 multiplied by the quantity x plus 1. And so if you notice, these two, this y equals x minus 2 and y equals 3x squared plus 4x minus 1, these are written in what we called standard form. This last one here is what's written in factored form. And this is going to be critical for us for today because we're going to actually be looking at how to sketch cubic and quartic polynomials. Now, you might be thinking, it's like, hey, I kind of know how to factor a quadratic, therefore I should be able to sketch what it looks like. Am I going to learn how to factor cubics or quartics and be able to go from there? Yes. Not today, but soon. And in general, when I say that we're studying cubic and quartics, what I mean is that we're going to be studying, say, degree 3 functions or degree 4 functions. And when I mean degree 3 or degree 4, these are the largest individual term with the largest exponent value. So these can appear in one of these two forms. So we have the two here, y is equal to 2x cubed minus 4x squared plus 5x minus 1. This, along with y is equal to x to the power of 4 minus 2x to the power of 3 plus 3x to the power of 2 plus x minus 1, these are written in standard form. Not particularly useful information in terms of trying to understand them beyond, say, what the leading coefficient is. That's quite helpful. What we're hoping to have a look at are going to be like the two on the right. this y is equal to, in brackets, x minus 1 times x minus 4 times x minus 8, and this y is equal to x plus 5, and so forth. So this top one has 3 brackets, and they are both what we call in factored form. And the first one here has like essentially 3 brackets with x minus whatever. This is what we call a cubic, or what we would say a degree 3. The bottom one, y is equal to x plus 5 times x plus 2 times x minus 1 times x minus 4. This is a quartic, or if you prefer, a degree 4. And just made a little note, cubic polynomials have degree 3 and quartic polynomials have degree 4. Now, it's worth noting that for our course, the MCT4C, the most we go up to is, for studying purposes, is degree 4. But this, the information I'm telling you can easily be extrapolated to higher degree polynomials. And typically in other courses, if we were to study these, we tend not to go above 6 or 7 because at some point it just becomes too lengthy for us to go through. And so let's have a look. So again, as a point of review, the leading coefficient is the coefficient of the term that is used to determine the degree of a polynomial function, and it could be positive or negative. And so when I talk about the leading coefficient, I have something like, say, 7x to the power of 4 minus 3x squared plus 3 minus 10, and this is, say, y equals. The leading coefficient would be the 7. So we'll call it the leading coefficient, which we'll call just leading LCF, leading coefficient. We'd say that the leading coefficient here is positive 7 specifically. And we care about whether that value is not 7, but we care about whether it's positive or negative. So we just say, oh, that's a positive for clarity purposes. Okay. And so what I care about for example 1 is we would like to determine the degree, the type of polynomial. And remember, type of polynomial means, is it linear, quadratic, cubic, or quartic? And the sign of the leading coefficient. And again, this is just so that way when I make a brief aside and say we're going to study this cubic, you should already be thinking of a set of ideas or constructs surrounding this, such that you should know that cubics have, say, 3 x-intercepts, and as well as the general behavior, what this looks like. The analog to this was when we were studying quadratics. You know, quadratics are U-shaped, they go up or they go down, and so forth. Okay. So for letter A, we have y is equal to 3x minus 1. So this is a standard line. So we would say that this is linear. The degree of this, we would say, is a degree 1. And the leading coefficient, and specifically the sign of the leading coefficient, is positive. Okay. If you want to, you could just write positive 3, like that's fine as well. But I just want to make a note that you're going out of your way to say that, yes, it's a positive 3 because it comes from here. For letter B, we have y is equal to 3 multiplied by, in brackets, x plus 2. And again, it's worth noting that this is still linear. The degree is still 1. And the leading coefficient is positive. In this case, still positive 3. Now you might be saying, hey, why did you kind of bring up the same function? Well, the reason why I did that is because the kind of functions we're going to be studying today are going to look like this. They are in factored form. And so I don't want you to try to expand these out. So I know that you know that 3 multiplied by x plus 2 is the same thing as 3x plus 6. You should just be able to quickly identify that the leading coefficient here is a 3, and this happens to be in factored form. Okay, let's continue on. Letter C, we have y is equal to 7x to the power of 3 minus 4x minus 9x to the power of 4. So it's written out of order, so we can go ahead and just write that in the correct order. So this is going to be y is equal to 9x, negative 9x to the power of 4 plus 7x to the power of 3 minus 4x. And so here, this thing is a quartic polynomial function. The highest degree is 4, and the leading coefficient is negative. And if you so like, you can say specifically that it's negative 9. Okay, and again, that just comes from, we have a look at the leading term. We can see, perhaps I don't want, when I double highlight here, we don't want to do that. We'll just single highlight. So we're looking at the leading term, and we can see that the leading coefficient is negative 9. And I should mention as well that we care about the leading coefficient, but another term you might run into is something called the leading term. And all that means is what's the biggest, the largest degree on the exponent. And so in that case, it'd be 7x to the power of 4, for example one from earlier. Okay, for letter D, we have y is equal to negative 5 times x to the power of 4 plus x to the power of 3 plus 2x. It's in proper order, but we can see that the largest degree term that appears is a degree 4 term. And so this will be a quartic. It'll be degree 4. And it's has a leading coefficient of a negative. And if you're so inclined, you can see that it's negative 5. So an important skill for talking about polynomials is you kind of want to see what kind of function you're dealing with. So when I look at this, the letter D here, and I see y is equal to negative 5 times x to the power of 4 plus x to the power of 3 plus 2x, I immediately think, this is a degree 4 or quartic negative leading coefficient. These are the things that matter. Okay. What about letter E? We have y is equal to x minus 2 multiplied by x plus 1. So it's worth noting that this is in factored form. Okay. So we know from the study of the lesson of last time that this is quadratic, which means by definition, it is degree 2. And for the leading coefficient, we can see that it's positive. And specifically, if you're curious about it, it's going to be a 1. So why is it a 1? Well, we have y is equal to x minus 2 times x plus 1. If we were to multiply this out, we would have x times x is x squared, plus x minus 2x minus 2, which is x squared minus x minus 2. So if we were to expand this out, which is what we normally don't want to do, but if you wanted to, the key thing to pick up is that the value of the, when looking at the leading term, the value of the coefficient is 1. And you can kind of pick that up from the start that there's nothing in front of those x terms, and consequently, you know that it's positive 1, because positive 1 times positive 1 is just 1. Okay. What about letter F? We have y is equal to negative x minus 1 times x plus 2 times x minus 3. So again, we can see that this is a cubic, okay, because we have 3 x terms all multiplied by each other. And because it's cubic, we note that it's a degree 3. And the leading coefficient is going to be negative. And if you're so inclined, we'd say that it's negative 1. Because the same idea, since it's negative times x minus 1 times x plus 2 times x minus 3, we can see we have a negative sign here. But then all of the other x values are positive. Hence, if you were to multiply it out, the leading term would be a negative x to the power of 3. Okay. For letter G, we have y is equal to 5 times x plus 5 times x plus 2 times x minus 1 times x minus 4. So just like before or above, you should note that this is in factored form. Okay. And we have 4x terms multiplied together. So this is going to be a quartic, degree 4. And it's going to have a leading coefficient of positive 5, or I guess I should be consistent and here and write that it's going to be positive, specifically positive 5. So last one, we saw this one from last time. If you have y equals 6, there's no variable terms here. This is actually what we call a constant. The degree on this is 0, but it still has a leading coefficient of a positive value, and specifically it's just 6. So if you wanted a quick sketch of what this one looked like as a review, this is a horizontal line that passes through 6. So there it is. So being able to identify what kind of functions you're working with is important. And so we're going to have our first look at what these things look like. So we're now going to be talking about the role of k in polynomial functions. So f of x is equal to, and this is kind of, instead of having from earlier where I had like say a sub n, whatever, basically it's just some k value multiplied by all of its products. And this is, at this point, this is true if this is an odd degree or an even degree, depending on what you want to look at. But for now, this is kind of how we write it. If we were just talking about cubic, we would know that it'd be, say, k multiplied by x minus x times x minus another factor on the end of it. But in general, this works for any polynomials. Okay. I saw a minor typo here, so let me fix this up. There should be k is less than 0. So if k is less than 0, the function decreases. So I'll put this here. It decreases, increases, and then decreases again. So this green section, where if you trace your finger on the function from left to right, going down means that it's decreasing. Going up means it's increasing. On the next lesson, I actually explicitly show you how to write the notation for increasing and decreasing. For now, I just want you to be able to sketch what these look like. So cubics in general look like this. They will have slightly different shape if there are less, say if you don't have as many x-intercepts, they'll look a little bit different. But if you have 3 different x-intercepts, it'll look something like this. Now, it could be raised up a little bit or raised down a little bit. So if you have a look at this graph on the left side here, suppose I had y is equal to x minus 1, x plus 1, x minus 2. You can see it has this general, like it kind of squiggle. It goes up, down, back up. Now, if you notice here, I can now just suddenly add like a plus 6 to this, and this will shift the function upwards. And you can see that this cubic still goes up, down, and up, but now it only has 1 x-intercept. Okay, so just know that for cubics, and I'm pretty sure I state this later somewhere, but if not, I'll say it now. Cubics can have 1 to 3 x-intercepts. Okay. So when the value of k is greater than 0, so here what I showed on the graph, and if you want to, I can put a little negative sign here and flip it upside. So if k is greater than 0, the function, and again, I'll highlight this in red for us, will increase, decrease, and increase again. Okay, that's just in general what they do. Quartic, here the value of k is 0. Is less than 0. And again, we're talking about functions like, say, y is equal to k times. Sorry about that. About to silence my phone. X minus, say, capital A times x minus capital B times x minus capital C and x minus capital D. Okay, so they have 4 factors, 1 factored, so it looks like this. So a nice way to describe the quartic, it kind of looks like an M, or if you prefer, a W when it's the other way. Okay, so you can see here when the k value is less than 0, it kind of has this M structure. So in this case, we increase in 2 locations and we decrease in 2 locations. And when k is greater than 0, we still decrease in 2 locations and we increase in 2 locations. Now it's worth noting that, again, if I was trying to sketch on the graph here on the left, okay, so here's again what it looks like in general. Just kind of sort of like a weird W or an M or something like that. That's what they look like in general. Okay. So far up to this point, I've only covered cases where we had single factors of x. Meaning it's just, if you notice on the left, all of these individual x-intercepts are all different. But that's not always going to be the case. Okay. So in general, the zeros of polynomials in function factored form are as follows. So here, this came from the textbook as well. We have linear, quadratic, cubic, and quartic, which is kind of what I summarized earlier. Okay. However, there is an exception to this, is what happens at the following. So suppose we have f of x is equal to x minus 2 to the power of 3 times x plus 1. So this is going to be a quartic function. The degree on this is 4, and we would say that the leading coefficient is positive. So you might be thinking, oh, why is this a quartic? There's only 2 factors. Well, if you notice here, we have x minus 2 to the power of 3, which means what this function actually looks like in factored form will be x minus 2 times x minus 2 times x minus 2 times x plus 1. So we have 4 x values altogether. So I wrote a little paragraph here in case you just get my notes because you can't watch the video, but that's why I'll just read this for the moment. We can see that x equals 2 and x equals negative 1 are the roots of this polynomial. So meaning that if you want the x-intercepts, there they are. A polynomial has a repeated root at x equals 2. You've heard of this before, but not using this notation. Okay, the root x equals 2 would have, we say, multiplicity 3 or order 3. Depending on what textbook you read through, they will use these interchangeably. And the multiplicity of the root affects this, the shape of the graph. It's worth noting that at x equals negative 1, this does have a multiplicity of 1, but we don't really notice that. We only talk about typically multiplicities for roots of order 2 and above. So for example, in these ones that we had to look at earlier in example 1, say for questions E, F, and G, all of these x-intercepts would be multiplicity 1 because there's no power of 2, power of 3. So you might be wondering correctly, what does this look like? Because you said it affected the shape of the graph, and I did. And so to do that, I should first show you what x to the power of 3 looks like on a graph. And so you can see here, this is what x to the power of 3 looks like. It's not quite just a straight line. It kind of comes up sharply, and then at x equals 0, bends, and then increases sharply again. And if I were to say make it x minus 2 all to the power of 3, you can see we just kind of shifted it over 2 units. But again, it still has that familiar S shape. Okay. Now, if I tack on an x plus 1 term into here, if you notice, the graph maintains its that little curve here. Here it is. There it is. So you can see here at x equals -1, it just passes through. And at x equals 2, it has that multiplicity 3 where it S shapes its way through. In general, if you have a order 3, that means the graph will S shape its way through. And if it's order 2, it'll do something called a bounce. You've actually seen this one before. So remember, you did study these ones in quadratics. So if you had like x minus 5 to the power of 2, we can see that that just creates a bit of a bounce there at that location. And if I were to tack on, say, an x minus 6, that's not a good example. Let's type in x minus 7. You can see there's still that bounce that occurs there. But again, it still maintains its cubic structure. Okay? All right. So example 2, we're going to determine the zeros and their multiplicity. So, and again, for our purposes, we're going to just note multiplicities of things of degree of order 2 and above. So here we have y equals x minus 4 and x plus 5. So we can have the case that x minus 4 is equal to 0. So x equals 4. And we have x plus 5 is equal to 0. So x equals -5. And for completeness, I'll just say that these are multiplicity 1. And again, we don't normally write this, but this is the first time we're learning about it, so I'll write it for this one. Similarly, for letter B, we have a cubic. We have y is equal to, in brackets, x plus 1 times x minus 2 times x minus 5. And so correspondingly, the x-intercepts are going to be -1, x equals 2, and x equals 5. So again, you set each of the factors equal to 0 and solve. So all of those happen to be multiplicity 1. They just pass through normally. Okay. What about letter C? We have y is equal to x minus 2 squared times x plus 1. So here we have x is equal to, so I have here x minus 2 equals 0. So x is equal to 2 is one of our answers, but afterwards we'll write the term multiplicity 2 because there's a 2 up there. And in fact, I'm going to color code this for us. So we'll say that this is multiplicity 2. Okay, we also have another x-intercept at x plus 4 equals 0, so just x equals 4, and that's normal multiplicity 1. Now, I said we wouldn't study more than above quartics, but I had to have one example of this just to kind of show you what this looks like. For letter D, we have y is equal to x minus 4 to the power of 3 multiplied by x plus 2 to the power of 2 times x minus 1. So already you should be thinking, well, the corresponding x-intercepts are x equals 4, x equals negative 2, and x is equal to 1. At x equals 4, we would say that this is multiplicity 4. At x equals negative 2, sorry, not 4, 3. At x equals negative 2, the multiplicity is 2. And then at x equals 1, it's just 1. But again, if you so wish, there's nothing wrong with this, but you can write multiplicity 1. You might be thinking, hey, is that a degree 6? It is. In fact, we can graph what this looks like, because with the power of decimals, this is pretty easy, pretty quick for us to graph. And so we go type in x minus 4, open off 44. We don't have space to write 44, times x plus 2 squared times x minus 1. As if to mess with the scale a bit here. Okay. There it is. And so you can see at x equals negative 2 is where this does a bounce off the x-axis. At x equals 4, you can see that it does an S shape its way through. And at x equals 1, it just passes through normally. Okay, so again, we can study polynomials. That's why I mentioned that we could study greater degree polynomials than this. But the reason why we didn't have to be too worried about these is because what we can learn about degrees 1, 2, 3, 4, we can easily apply to higher ones. Okay, for E, F, G, and H, we actually have the x-intercepts, or more accurately, we were given the graphs, and we just have to list off the corresponding x-intercepts. And so here, this is a quartic, and we have 4 x-intercepts here. And the x-intercepts appear to be negative 2, negative 1, 1, and 2. Now, if you want to be slick about this, you can write the x-intercepts as plus or minus 2, plus or minus 1, like so. For letter F, we have a curve that looks like this. But we have here 3 x-intercepts. That looks like x-intercepts of negative 3, negative 2, and positive 1. So no problem. For letter G, this is a cubic, because I should write what kind of functions those are. G, this one's a cubic. And this time around, we only have 2 x-intercepts. But if you notice, we've got that bounce there, right? So for x-intercepts, we have x equals negative 1, and we have x equals 2, order 2, or multiplicity 2, depending on what you want to call, depending on what you like to call it. Okay. For letter H, we could see that this is not quite quadratic. It's actually a quartic function. And it has 2 x-intercepts. And we can see that at this x-intercept of negative 2, this has multiplicity 3. And I ran out of space, so I'm just going to call it order 3, which is what I normally do for space purposes. So this will be 3. And then it has another x-intercept of just 1. Okay. So here what we're able to do is from the equations of graphs, we're able to list off their x-intercepts as well as their corresponding multiplicity or order. And we can also list off these x-intercepts from the graph itself. Okay. And I should mention for letter H, if I were to type in the equation for that, this looks like x plus 2 cubed times x minus 1. But then we got to make the whole thing negative. You can see this is already pretty close to what that graph looks like. So in fact, it's actually the exact same graph, just a different color. Okay. And so here, here's what we can say. So we're going to talk about characteristics of polynomials. But before I do that, I want to mention this little chart here, which is going to come in handy for us. So this is the Cartesian plane. Okay. So here's my x-axis. Here's my y-axis. This is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Typically, when we write quadrants, we use the Roman numerals. So 1, 2 is two lines, quadrant 3 is 3 lines, and quadrant 4 is this 1v. Okay? Typically, that's what we write, but you can also just write Q1, Q2, Q3, Q4. I'll know what you're talking about. And so what's so special about this? Well, I have this chart here about characteristics of polynomials. In general, if you have an odd degree polynomial, so these are things like that could be, say, this could be degree 1, 3, but then again, we could also keep going and say 5, 7, 9, whatever. If the leading coefficient is positive or negative, but in this case, we'll say, look, if the leading coefficient is positive, what happens? As x goes to infinity, y goes to positive infinity. As x goes to negative infinity, x goes to negative infinity. And all that's describing is where does the function start? Where does the function end? So here, if I were to say, as x approaches positive infinity, y approaches positive infinity, that's describing this part here, which I highlighted in red, the end of the graph. Well, we'll just do one at a time. And as x approaches negative infinity, the function approaches negative infinity. And so that's quite a lot to take in. An easier way to think about this is that the function starts in quadrant 3 and ends in quadrant 1. So it goes this way. When the leading coefficient of an odd degree polynomial is negative, that means it starts in quadrant 2 and it ends in quadrant 4. Okay? For even degree polynomials, and again, when I talk about even degree polynomials, we're talking about degree, for simplicity's sake, we'll say degree 4, degree 2, degree 4, degree 6, degree 8, degree 10, whatever. They both start and end on the same side of the x-axis. So as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y approaches positive infinity. Similarly, if the leading coefficient is negative, then that means that means as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches negative infinity. Again, that's clunky notation. What's easier to state is that if it's an even degree polynomial positive, then that means it has m behavior of quadrant 2 to quadrant 1. And if it's an even degree negative leading coefficient, And that means we go from quadrant 3 to quadrant 4. That's why I just include these two notations. Depending on what the book you read, they might use this top notation with the infinities, but most students have universally agreed that talking about the M behavior in terms of what quadrant does it start, what quadrant does it end is a much easier way to think about this. Okay. And so at this point, we're going to reference this chart and not committed to memory yet, but just for the purposes of the lesson, we're going to refer to this. And so if we have a polynomial, if we know what the degree is and we know what the leading coefficient is, then we know what the M behavior of this function is going to be. So where does it start? Where does it end? And so, for example 3, we're going to do the degree and sign of the leading coefficient. So we're going to use the degree and the sign of the leading coefficient to describe the M behavior. Okay? And the M behavior was this stuff. Where does the function start? Where does it end? Okay? Small abbreviation we're going to use for M behavior, we're going to call it just EB. Okay. So for A, we have f of x is equal to 3x to the power of 4 plus 4x to the power of 3 minus 5x squared. And so this is a degree 4 because that's the largest term with the greatest exponent. The leading coefficient is positive. In case you're wondering, it's specifically positive 3. Okay. And what does the M behavior do? Let me just have a look up here. For an even degree positive polynomial, we go quadrant 2 to quadrant 1. So it looks like that. So what I'm saying is, if I were to graph what this thing looks like, negative 3x to the power of 4, positive 3x to the power of 4, plus 4x to the power of 3 minus 5x squared. Here's what that one looks like. We start off in quadrant 2 and we end in quadrant 1. Okay. All right. At this point, this would be a great time for you to pause the video, go ahead and try these ones out for yourselves, and then see how you did if you're watching this on YouTube. Okay, so let's have a look at this now. For letter B, we have f of x is equal to negative 2x to the power of 3 minus 3x to the power of 2 plus 2x plus 1. So we can see here that this has a leading term of negative 2x to the power of 3. And so the degree on this thing is going to be a 3. The leading coefficient is negative, and specifically it's negative 2 in case you're wondering. And for the M behavior, so we're talking about a degree 3 negative. So degree 3, that's odd. That means it goes from quadrant 2 to quadrant 4. And we can just write it as Q2, right arrow Q4. And again, if we wanted to graph, just to confirm that this is what indeed this looks like, negative 2x to the power of 3 minus 3x to the power of 2 minus, plus 2x minus plus 1. Here it is here. We can see that this graph starts off in quadrant 2, and then it'll keep going down to quadrant 4 at the end. Okay, what about letter C? We have f of x is equal to negative 2 times x minus 4 multiplied by x plus 3. So already you're kind of looking at this, you're like, oh, this is a degree 2. This is a normal quadratic. So I guess we can label that if you're so inclined. The leading coefficient is going to be negative. And if you wanted to know, it's going to be -2. The end behavior, well, this is a normal quadratic that's upside down, but it's a even degree negative exponent, which means it starts in quadrant 3 and ends in quadrant 4. And so we can write the behavior as such. Quadrant 3 to quadrant 4. Lastly, but not leastly, we have f of x is equal to 2 multiplied by the quantity x minus 4 to the power of 2 times x plus 1. So we know that this is a degree 3, meaning that this is a cubic. Okay. The leading coefficient is positive, and specifically, we can see that it's +2. And the end behavior, okay, so this is a degree 3 positive, so we can see that it goes from quadrant 3 to quadrant 1. And this is definitely the lesson where we want to, like I said, become comfortable with just checking some of these things on Desmos just to confirm that they do the things we say that they do. And so when I type this in, oh, just shrank my x-axis a bit. There we go. So, especially once you deal with cubics and quartics, you have to mess with the y-axis sometimes because when your x-intercepts are farther apart, you end up going up quite high quite quickly. And so you can see that passes through at -1, and we've got a bounce at 4, which makes sense given what we were working with. Okay. The last section we're going to be looking at here is actually sketching some of these things. So we're gonna sketch 4 of them, and we can use Desmos to check these for us if you would like. Probably not this first one because it's going to go. No, we'll check the first one. So here, when I have a look at this one, I can see, and I've got y is equal to 2 times x plus 9 times x plus 4 times x minus 3. This is a degree 3. The leading coefficient is a positive number. In this case, it's 2. And so we have a degree 3 positive, which means it goes from quadrant 3 to quadrant 1. Now, I'm going to make a bit of space here because I didn't plan that one out. This has x-intercepts of x is equal to -9, x is equal to -4, and x is equal to 3. And so, if I were to do a sketch of what it looks like, and again, sketches and arc graphs, if you wanted to graph this, you would need to choose x values between x equals -10 to x equals 5 to be able to sketch this reasonably well. The textbook has an example where they graph what this looks like, and it's quite tedious to come up with all of the table values, but you can absolutely do that. It just takes quite a bit of time to do. And so we will come out here to -9. There's one of our x-intercepts, -4. There's another one, and 3. There's our last one. And so what do I know? My graph starts in quadrant 3. So that means it starts off over here and it ends in quadrant 1, which means it's going to end off over here. So the only way this makes sense is that we pass through x equals -9, down through x equals -4, and then at some point go back up to x equals 3. The only thing we're not sure of is we're not sure where these bumps are located for sure, but that doesn't matter because it's a sketch. It should roughly look like that. And so if I type in 2 bracket x plus 9 times, oh, not a second bracket, x plus 4 times x minus 3, I have to zoom out a bit here. This is roughly what the graph looks like. And if you notice here, on my graph, I didn't include a y-axis because in this case, our y-axis has to go all the way down to negative, looks like 200 to be able to graph this thing correctly, but that's okay. But we provided a reasonable sketch of what this looks like. Okay. So for example 4, for each of the following, we're going to state the M behavior, the degree, and the x-intercepts, and then afterwards do a sketch of what these things look like. So for A, this is a quadratic that we know and trust. Okay. And so we need we'll go with the degree first. So this is a degree 2. It's just a quadratic with two binomial factors multiplied together. I should say the leading coefficient is negative, right? Because there's a negative sign up front and all the other x terms are positive. The M behavior goes from, now this is a negative quadratic or negative degree 2 polynomial. So this goes from quadrant 3 to quadrant 4. And the x-intercepts in this case are going to be 2 and negative 4. And so when I make a graph of this, there's my negative 4, there's my 2. And this will be roughly what this graph looks like. Okay. If you want to get a bit more accurate, you could state in things like the y-intercept to help make your graph a little bit easier to read quickly if you so wish, but that's not necessary for us. For us, we're just showing you why it looks like the way it does. And again, to provide a graph of what this looks like, x plus 4. We got to work with the y-axis there. Here's our graph again. You can see it passes through at that point. Okay. For letter B, we have y is equal to x plus 4 times x plus 2 times x minus 3. So this is going to be a degree 3. The leading coefficient is going to be positive. The M behavior, and again, I'm just reading the chart from above, will be quadrant 3 to quadrant 1. And the x-intercepts are negative 4, negative 2, and 3. And so when we go ahead and sketch these in, there's negative 4, there's negative 2, and there's 3. We start down here, end up here. And so our graph will look something like this. Because it has to pass through at those x-intercepts, it can't pass through anywhere else, or else we would see it. Okay, next one here we have y is equal to negative 5x times x plus 3 squared. So here, this is a degree 3. The leading coefficient is negative. The M behavior, this is a negative odd degree cubic. So the M behavior will be quadrants 2 to quadrant 4. And this will have x-intercepts of 0 from this negative 5x and negative 3, and we'll call it order 2. And so a graph of this, okay, we have to pass through the origin 0 and negative 3. This is going to be order 2. And so we know the graph has to start in quadrant 2 and end in quadrant 4. So it has to pass through negative 3. And since it's order 2, that means it has to bounce off of it, come down, and continue downwards. And so checking this on our sketch here, negative 5x times x plus 3 squared. And you can see that that's what that looks like. Negative 3. Oh, sorry, slight mistake. That's why we check these. I had these, they should have been reversed, but that's okay. So we bounce off -3 and then down through 0 normally. We don't have time for this last one, so we'll take this up for tomorrow. And for now, I'll see all of you tomorrow, and best of luck.